First of all, what is a simple region? Similarly to what we did for double integrals, a simple region is going to be a region that such that one variable moves between two continuous functions of the other two variables. So for example, a simple region is going to be called of type 1 or an xy region if it lies between two continuous functions that depend on x and y. So in this case, C moves between two functions that depends on x and y over a certain plane region D. So here, if you pick x and y, then the C is going to be moved between two values of two continuous functions that depend on x and y. How we are going to do the integrals over these type 1 regions? Well, it's going to be pretty much the same thing that we did before. We are going to say, well, since C moves between these two variables, between these two functions, those two functions are going to be your limits of integration when you integrate with respect to C. You do that first, so remember, functions are integrated first, and then the resulting thing is going to have you're going to have a double integral that we already know how to compute. You can do that with type 2 regions. Type 2 regions are defined, or also called YC regions, are going to be defined of functions such that the x moves between two continuous functions that depend on y and c. And the way that you integrate again is you just put the two functions as your limits when you integrate first with respect to x. You have to be careful to always put the function that is lower on the bottom and the function that is higher with respect to x, of course. We have the type 3 regions that are going to be pretty much the same, but now with y moving between two continuous functions that depend on x and c. So the thing that we have here, that's why they are called XC regions. And again, you just integrate with respect to y, and in the lower part you put the lower function, and in the upper part you put the higher function. Let me give you an example. Suppose that we're integrating this function over the region E, and the region E is the solid between these two surfaces when y goes from 0 to 3. So first of all, we have to visualize how this solid looks like. So C equal to 2 minus x squared is a cylinder, parabolic cylinder, just like in the picture. Here we have it. Then we have C equal to x squared, that is another parabolic cylinder, but now it's opening towards the opposite direction, the parabolas. And the thing that we're doing is we're taking the region between those two and bounded by y going from 0 to 3. So that's the solid E. Now this solid E can be seen in a very different ways. First of all, I'm going to set it up as a type 1 region. So the thing that I'm going to say is the C is going to move between two continuous functions that depend on x and y. In this case, the two continuous functions is 2 minus x squared, and the bottom is going to be x squared. And the region that I'm going to integrate after that is going to be the region D, that now is a plane region that gives you a rectangle. So let me just tell you how I'm going to set it up. And the only thing that I'm trying to do is I'm trying to convert this into an iterated integral. So I use the triple integrals over type 1 region kind of like method, that is just put the functions that depend, that C moves between it, and then integrate with respect to C. So that's what I'm doing right now. And then I'm going to say, well, notice that the region D is a rectangle, so I can just integrate with respect to y and take the limits from 0 to 3, and then integrate with respect to x and take the limits from -1 to 1. So I take the integral, and I integrate with respect to c, then I plug in what c is equal to, then I kind of like FOIL that expression, and we move to the next one. Now when I have this expression foiled and I'm going to integrate with respect to y, I plug in what y is equal to. Notice I'm putting y equal to 3 and y equal to 0 in order not to get confused, since I am going to have two variables. Then I plug in what y is equal to 3 and y is equal to 0, and I obtain this. And then I integrate with respect to x, that is my last variable, and I'm going to plug in x equal to 1 and x equal to -1 here, and I am going to obtain that the answer is 12. You could have set up these in a different way. Do I get the same answer if I put it as a different region? So for example, here we can put it as a XC region. In other words, y is moving between two continuous functions that depend on x and c. Well, these are constant functions, so by default they depend on x and z. And the answer is yes, well, because first of all we integrate with respect to y from 0 to 3, and then we plug in what is the region D. Now the region D, notice that the region D moves, the C moves between x squared and 2 minus x squared, and that's what the second integral is going to be equal to. And the reason is because, remember, the functions go inside. And then the last one is going to be minus 1 to 1, the x's, where it's moving. So now I do the integral. I integrate first with respect to y. Here is already the integral with respect to y. Then I integrate with respect to z. I plug in back here, and then I am starting just to FOIL and then integrate with respect to x, and the thing that I end up is again with the number 12. That was our result of the previous integral, or well, the same integral, just integrated in a different way. Let me move on to volumes and triple integrals. So the volume of a bounded region in space, if you remember, the area was the double integral of the region of the function 1. And this is going to be more or less the same when you take the function 1 and now you take the triple integral over the region E, then the thing that you are going to obtain is a volume. So let me give you an example. Suppose that we want to use triple integrals to find the volume of the solid bounded by this plane and the coordinate planes. So we have, this is the solid E, and now notice that the bounds are going to be the coordinate planes and this yellow plane, that is 1 minus x minus y. So notice that we can set it up as an xy region just like this. So let me continue. Now the thing that we have is the region D. Now it's this triangle, can be also set up like this. The x moves between 0 and 1, and the y moves between 0 and this line over here, that is y equal to 1 minus x. Once we have this set up, then the volume is going to be the triple integral of the function 1 over E dv, and that's going to be first integrating with respect to c, that is equal to this, and then we're going to integrate with respect to y. Why? Because y moves between two continuous functions that depend on x, and then with respect to x, because the x is the one that is moving between numbers. So the thing that we have is when you take the evaluation of all these integrals, integrate first with respect to c, the function 1 gives you c, and then you plug in, then you integrate with respect to y, and then you end up here integrating with respect to x, and it gives you 1/6 as the answer. Then I'm going to finish to give you some properties of triple integrals. One of the common properties is if you take the triple integral of a function and you divide by the volume of the solid, the thing that you will have is the average value. Other properties that I'm not going to list here formally, but a lot of the properties for double integrals can extend to triple integrals like this. For example, the integral of the sum is the sum of the integrals, and also you can take constants outside. I'm not going to, I didn't put it here, but you can split your region into two regions and take the integral of each individual region, as long as these two regions don't overlap except for the boundary. And if one function is bigger than the other one, then the triple integral is going to be less or equal than the other.